Hello everyone, this is Ketish here. In this video, I'm going to go through the AQA Combined Science Physics Paper 2 Higher Tier. Question number 6 is on forces. This is from the 2023 paper. Question number 6. Figure 9 shows a child dropping a stone into the water. So you have a child with a stone there. 6.1. When the child drops the stone, it passes the child's feet with a velocity of 3.1 meters. So when it's here, let's say that's the initial velocity is 3.1 meters per second. The child's feet are 6.3 meters above the water. So from there to, this should be a straight line. Let me see if I can draw a straight line. There you go. And that's 6.3 meters. And they are asking for the final velocity. Calculate the velocity of the stone as it hits the water. So final velocity is what they are asking. Acceleration due to gravity is 9.8. So 6.3 is the distance. Use the equation. So you have to use one of the SUVAT equations for this, which is v squared minus u squared equals 2as. S is the distance, a is the acceleration due to gravity, and u is the initial velocity. So v squared minus, let's substitute the values. U is 3.1, so that'll be a squared, equals 2 times 9.8 times 6.3. So rearranging it, or before I rearrange it, let's simplify this. So 3.1 times 3.1, which is basically the square, that would give me 9.61 equals, let's find the value on that side, 2 times 9.8 times 6.3. That gives me 123.48. So v squared is 123.48 plus 9.61. So add that to 9.61. That's 133. V squared is 133.009. So v is the square root of that number, 133.09. So square root of the answer is 11.54. They want the answer in two significant figures, which carries a mark. So that would be 12. Next question. Let's get rid of the calculator. Velocity is a vector. Describe the velocity of a stone as it falls through the air. Assume there is no air resistance. Now, because velocity is a vector, it should have a magnitude and a direction. So you need to describe what is happening to the magnitude and the direction of the stone's velocity as it falls through the air. So the magnitude, obviously, because it's speeding up, the magnitude is increasing uniformly, but the direction remains the same. So direction remains constant, which is downwards. Next part, 6.3. Figure 10 shows the stone just after it enters the water. As the stone moves through the water, the stone slows to a constant velocity. So it has maximum velocity when it enters the water. Now, there's weight acting downwards, but there's also going to be drag acting upwards. Now, because the velocity when it hits the water is maximum, the drag is also going to be maximum or higher. But as it slows down, the drag also slows down, which means the stone now falls at a terminal velocity. So that's why terminal velocity is constant velocity here. So as the stone moves through the water, the stone slows to a constant velocity. Explain why. It will move at constant velocity when the drag is equal to the weight of the stone. So drag is greater than weight at the start. So there's a resultant force acting in the opposite direction to the velocity, causing a deceleration. So drag is greater than weight at the start. So there's a resultant force acting in the opposite direction to the velocity, causing a deceleration. As velocity decreases, the drag also decreases until the drag is equal to the weight, at which point the velocity will be constant. That brings us to the end of question number 6, and I will see you in question number 7.